Welcome to my lab report on Lab 1, Constant Velocity. The purpose of this lab was to observe the motion of an object moving at a constant velocity, then to create an observational and computational model to predict the object's motion over time, and finally analyze the relationship between the object's position, velocity, and time. Core physics principles for this experiment would be Newton's first and second laws. Newton's first law states that an object at rest remains at rest, and an object in motion remains in motion at constant speed in a straight line until acted upon by an unbalanced force. Newton's second law, otherwise known as the momentum principle, just states that force is equal to the change momentum per change of time, or force equals mass times acceleration. Key equations for this lab are the position update equation, the velocity update equation, and the momentum principle. A quick preview of my results. And the two models that were made during this lab were the observational model, which was made via tracker with hand-plotted points to determine the change in position during each frame of the video of the experiment. And afterwards, the computational model was made with GlowScript code, which would predict the object's expected motion using the position update and velocity update equations. For this experiment, firstly, there was a recording of a water bottle rolling across a table at a constant velocity. Then this video was uploaded to Tracker and calibrated the distance traveled by the bottle to be 1 meter. And core computations was after this video was taken, the water bottle's initial position was 0.000 meters. The initial velocity was negative 0.500, and delta t was 0.03 seconds per frame. And then the computational model was created in GlowScript utilizing these calculated values along with the position update equation. Here is a video of the experiment now. How exciting! Shown below is the code used to create the computational model. Taking the water bottle's initial position to be at the origin, or 0.000, and the bottle's initial velocity to be negative 0.5, which was found by taking the calibrated 1 meter and dividing it over the course of 2 seconds, and as the water bottle moved to the left of the origin, it moved in the negative x direction, leading to negative 0.5 meters per second. T started at 0, and delta t was calculated by taking the 2 seconds of video length and dividing it by the 60 frames within the video, giving us 0.03. Over the course of this time duration, there was no additional force added on to the water bottle, causing F net to be 0.000. This led to the ball's velocity to remain constant, as there's no additional acceleration being added on to the bottle velocity. With this constant velocity, the bottle's position was then updated by taking its previous position and adding the velocity times delta t. And as delta t advanced, all of these plot points were plotted onto a graph, such as this one, which shows both observational and computational model showing the bottle moving steadily in the negative x direction. However, the observational model is not as straight as the computational model, which can be attributed to errors in plotting the exact center of mass on Tracker. What if the axes were flipped? If the origin were placed in a different position so that the water bottle moved in the opposite x direction, the models would flip across the x-axis. However, the data recorded would not change, only the direction of motion. What does it mean? For the computational model to work accurately, it needs the net force of the system, in this case the water bottle, to be 0. Assuming the water bottle was placed on surroundings, the table, with negligible friction, a net force of 0 could be achieved by considering the force of gravity pushing the bottle into the table and the reciprocating normal force of the table pushing back into the water bottle. This leads to a net force of 0, as opposite forces of equal magnitudes will cancel each other out mathematically. In conclusion, this experiment showcased the relationship between constant velocity and the position of an object over time. With a constant velocity, the displacement of an object will move away from the origin at a constant rate. These principles were also shown to be easily represented through iterative code that calculates the change in position over a given period. Thank you for watching.